Okay, here we go. So we're still doing Khovanov homology. We're still following drawbn.net/mo13.
I think you're not screen sharing.
And I'm not screen sharing. I remember that there were 2 steps and that I've done only one of them, but I couldn't remember what was the other step.
And you also wanted to switch your camera to the other one, right?
Oh my God! Yeah, what a bad. Okay, good. Okay, so thank you. Now, okay. So a few comments. So homework 3 is already on the web. Homework 2 is due tonight. Hello, Jesse. And I hope today to tell you what is the most disturbing open problem about Khovanov homology, but we'll get there towards the end. And I just want brief reminders. So we had a vector space V generated by 2 vectors V plus and V minuses whose degrees are plus and minus 1, and whose purpose in this game is to have dimension the invariant of the R naught. Then we define the Khovanov complex to be, well, circle to the k goes to V tensor to the k, and then, well, basically by the rule in this picture, and I think I talked about it enough, so I don't want to say more, but I wanted to say that what was missing was to convert this picture into a commutative diagram, meaning to put differentials on the maps on the edges so that all faces commute. So there are 2 types of edges: the edges on which 2 circles combine into 1, and the edges in which 1 circle combines into 2. So we need 2 maps, and the maps are a map M, I call them M, going from V tensor V into V, and delta going from V into V tensor V. And last time we figured out the requirements, and they were that the degree of both maps be -1, that M will be commutative and associative, and we said what that means, that delta will be co-commutative and co-associative, and we said what that means, and that there is some funny compatibility condition between them called Frobenius Compatibility, and we said what it was. Okay? And then we started looking at what maps can we write such that the degrees are right, such that M is commutative, and such that delta is co-commutative, and we ignored the other conditions, and the conclusion was that the maps are, or that the map M is given by V plus tensor V minus is equal to a multiple of V minus. V plus tensor V plus is equal to a multiple of V plus. V minus tensor, and furthermore, V minus tensor V plus is going to a multiple of V minus, and in fact, necessarily, so these 2 multiples must be the same by commutativity. And delta is given by V plus is going to a multiple of the combination written here, and V minus goes to a multiple of the combination written here, and then luck happens, and if you take all the multiples, all the coefficients to be 1, you get an interesting theory. Not quite the only theory, but in fact the most interesting theory. Okay? So, what do you need to check? In principle, you only need to check, well, I mean, not in principle, all you need to check is those conditions that I haven't checked yet. Namely, we have to check that M is associative, that delta is co-associative, and that the funny Frobenius compatibility law holds. So let's call these things 1, 2, and 6, and then try to do them. So 1 is the product given by this law is associative. I don't know, that's the most boring check that you can possibly do. I don't know, you need to check that V plus times V minus times V plus is equal to V plus times V minus times V plus. Okay? I mean, sorry, I think I wrote it with unnecessary parentheses. So you just look up the multiplication and you check, it works. Okay? And then you need to check the same for all the other possibilities. And there are 8 possibilities, I suppose. Since it's commutative, there are fewer than 8 possibilities. So, I mean, you need to check some things. It's completely routine. It's a complete waste of time. The only thing I want to say is that it checks. Okay? Maybe it will be even easier if we noted that V plus is the identity element. So V plus times anything is back to the thing itself, right? V plus times V minus is V minus, V minus times V plus is V minus, and V plus times V plus is V plus. So V plus is an identity. And so many of the checks are superfluous, okay? And in fact, the algebra, so if you look at the vector space V, sorry, I don't know why it came out funny. Oh, I know, I'm running a large program in the background and it's slowing down my computer. Sorry, today I didn't set up everything correctly. Let me pause it. Okay, so now my computer will be a bit faster. Sorry about that. Okay, so so claim, just a minor claim, just good to know. If you look at the vector space V with the multiplication M, well, that's an algebra, and I claim that this is the algebra let's work over Z for no reason whatsoever. So this is the algebra of polynomials in the variable x modulo x squared is equal to 0. So it's really a simple thing. And the isomorphism, so this is isomorphic, and the isomorphism is 1 goes to V plus and x goes to V minus, and you can just check it, right? So 1 is the identity, and the only remaining product is x times x, which is 0 here and also here. So it's a really simple-minded algebra. The second property to check is that delta is co-associative. So you know, again, let me do it on only one or you know what, let me do it on both, okay? So I need to check that if I take V plus and apply to it delta, and then take the result and apply to it either, so let's write the result. So the result is V plus tensor V minus plus V minus tensor V plus, and then I take the result and apply to it either 1 tensor delta or delta tensor 1. I need to know that both results are the same. So if I apply 1 tensor delta, I get V plus times the V minus becomes V minus, because V minus goes to minus minus, plus now I apply one tensor delta to the second term, and I get V minus times V plus V minus plus V minus V plus, and you open parentheses and you do the same thing and you find that they're equal, and so we're done. I mean, I'm only showing what you need to check. I don't want to actually check the, it's too easy. And then there is property number 6 to check, and I called it property number 6 because if I remember correctly, it's question number 6 on your homework assignment today. It's very easy. I just wanted to check it, to put it, okay? I might be confused and it's really number 5. I don't exactly remember. Okay? Good. So, Khovanov homology is fully defined. Okay? I don't know yet that it is an invariant. So, let me prove to you that the homology of this complex that I wrote before is an invariant. But I need a tool. So, the tool is basically, okay, if you look at Reidemeister moves, then Reidemeister 1 and Reidemeister 2 have a complicated side and an easy side. So the complicated side, so like if you're talking about Reidemeister 2, the complicated side is this side, and the easy side is this side, right? And the complicated side is going to have a much larger Khovanov complex than the easy side. Like it will be, well, there are 2 more crossings, so the cube will be 2 dimensions bigger, so you'll have 4 times as much spaces in it. Okay? So what you need is a tool that if you have a big complex, and then you are able to cut off parts of it and reduce it to a smaller one. Okay? Basically, you need a tool to look at a complex and say, these parts are irrelevant, I can cut them off and get a smaller one. Okay? So this is the following theorem, which is really easy. Okay? So the theorem is the following. So suppose C prime, a subset of C, so this is calligraphic C in as much as I can do it. So suppose, suppose C prime, a subset of C, is an inclusion of complexes. So just to be precise, what does it mean? It means that you have the complex C, the big complex C. So let me write it here. So C is some sequence of chain spaces. CR goes to CR plus 1, goes to, comes from CR minus 1, and so on. And C prime is a subcomplex. So there is a subset C prime R minus 1 of CR minus 1. There is a subset CR, C prime R of CR. There is a subset C prime R plus 1 of this, such that the differential of the C complex restricts to C prime. Okay? Now, whenever you have such a situation, you can define a third complex and it is the quotient. You can define C modulo C prime, and C modulo C prime is simply C, the chain groups are CR modulo C prime R, etc. And you can check that this is also a complex. Okay? And then the theorem says the following. Well, it has two parts. Part A, if the complex that the smaller complex is has no homology, then the quotient has the same homology as the original complex. So if I'm sorry. So if the homology of C prime is equal to 0, and linguistically we say that C prime is acyclic. Okay? So if the homology of C prime is equal to 0, then the homology of C is then cancelling out C prime, doesn't change the homology. So the homology of C modulo C prime is equal to the homology of C. And part B of the theorem is likewise if when you cancel C prime there is no homology, then it means that all the homology was in C prime. Okay? So if the homology of C modulo C prime is equal to 0, then the homology of the full complex is equal to the homology of C prime. Okay? So can somebody give me a quick proof?
You just look at the long-exact sequence of chain complexes from here to here.
Exactly. So, question, how many of you have seen the long exact sequence of a short exact sequence? Sorry, the long exact sequence of a short exact sequence. Okay. So, I will skip the review. But just tell you that such a thing exists. So, so let me start with, let me at least state it. So, whenever you have a short exact sequence of complexes, so in our case it's C prime goes to C goes to C modulo C prime, and this is an exact sequence because, well, quotients are exact sequences. So whenever you have such a short exact sequence, there is a corresponding long exact sequence. So whenever you have such a thing, there is a corresponding long exact sequence of homologies. And let me just write it. So it goes like this. R minus 1 homology of, you know what, let's start with level R. So the rth homology of the complex C maps into the rth homology of the complex C modulo C prime, and there is a map into it from the rth homology of the complex C prime. And then, I should have left more space. And then there is a similar thing with the R minus 1 homologies. Sorry, here it's C modulo C prime. And a similar thing with the R plus 1 homologies. And they all fit together into a long exact sequence. So there is a map going from here to here, and a map from here to here, such that the sequence you thus get is exact. Okay? And now there are two cases to check. So let me do case A in green. So case A was that the homology of C prime was equal to 0. If the homology of C prime is equal to 0, then this is 0 and this is 0. And so you get 0 goes to homology of C, goes to homology of the quotient goes to 0, and that's an ultra short exact sequence. And if you have 0 goes to A, goes to B, goes to 0, it means that A and B are isomorphic. So this is isomorphic to that, which is what we wanted to show. And case B in red, so if the quotient has vanishing homology, then this is 0 and this is 0, and then these two are isomorphic. Okay? So I would have given this proof, I mean the details, I would have given the long exact sequence of a short exact sequence as an assignment, except I suspect that many of you have seen it. And the other thing is that this is one of the most annoying proofs in mathematics. It's like, it's very easy to do by a diagram chase, and it's the most painful thing in the world to write it. And it's only painful, it's pain with no benefits. So let's not do it.
You could give this one as the next assignment.
No, I will not, because again, it's pain with no benefits. So, I can now tell you about invariance. It's really, really easy. There is invariance under Reidemeister 1. So, okay. Let me, is this large enough or should I magnify it? Magnify or not?
Magnify.
Magnify, okay. Magnifying actually is a bit harder than I said, because I need to make room for it. So first of all, let's move invariance under Reidemeister 2 a bit below. And then now I can look at this. Oh, come on. I can look at it and magnify. Good. Okay. So, so here is the complex of the left-hand side of a Reidemeister 1 move written schematically. Okay? So, schematically, you have two smoothings of the left-hand side of the Reidemeister 1 move, and one smoothing will give you this picture, and the other smoothing will give you that picture. Okay? And so now the way I wrote it in this class, I've incorporated the degree shifts into the definition of the complex. When I wrote it, where I copied this diagram for, the degree shifts were not incorporated, so I have to apologize for this. Really, you should ignore this degree shift. It's already built in the way I wrote it. Okay? So likewise, you should ignore this degree shift. Okay? So now, this is my complex. Now, the complex is actually much more complicated because say this knot had n crossings, then after I smoothed one, you still have n minus 1 crossings. So this is really an n minus 1 dimensional cube. And this is really also an n minus 1 dimensional cube. And these two cubes are lying on top of each other, and there are maps between them. These are these maps M. And then I flatten everything to a single complex. Okay? But still, so this picture represents something quite complicated. But still, the map that the edges that connect these 2 to the n minus 1 vertices to these 2 to the n minus 1 vertices are all edges in which a cycle is merged into another one. Like the tiny cycle gets merged into whichever big cycle this might connect to. Okay? So all of those edges that go from, what have I done? Oh, what have I done? Sorry. I'm sorry. All of those edges that go from the one cube to the next are M edges. And now I claim that this complex has a subcomplex. And the subcomplex is C prime. And I'll just indicate it with, again, a schematic language. So the subcomplex is the subcomplex in which you make no changes to the term on the right, so to the n minus 1 dimensional cube that corresponds to the 1 smoothing. And in the n minus 1 dimensional cube that corresponds to the 0 smoothing, there is always a single cycle. This single cycle corresponds to a copy of the vector space V. Right? Now, which means that every element in this chain group will have either a V plus associated with this single cycle or a V minus. Right? Basically, the chain group associated to a bunch of cycles, so if you have 3 cycles, the corresponding chain group will be V tensor V tensor V, which really means that you end up writing on each cycle either V1 or V minus 1. So either V plus or V minus. Okay? So let's look at the subcomplex in which this cycle is marked with V plus. It's a subcomplex, first of all. It's a subcomplex because basically because the map M maps whatever is here to something here, and even if you look at the subspace here, it goes to a subspace here. And since I took the full thing on the right, this is this is still a subcomplex. And furthermore, all the other differentials within this cube on the left, so this is really an n-1 dimensional cube, but all of them have to do with other tensor factors. So they preserve the fact that this special tensor factor is labeled with V+. So C prime is a subcomplex. Now what is the quotient subcomplex? The quotient complex. So if I mod out all the spaces on the upper, on the second layer, on the right layer of the cube, with all the spaces with themselves, the quotient is 0. Okay? And if I mod out by this space, by the space in which this cycle is marked with a plus, okay, the quotient is the same complex with this cycle marked either with a V plus or with a V minus, but when it is marked with V plus, it is set to 0. Right? That's the meaning of being in a quotient. Okay? Now, if you look at the complex C prime, the complex C prime is acyclic, has no homology. Why? Because M is the identity map. If this circle is mapped with V plus, and remember that V plus is the identity of the algebra, and the map from here to here is multiplication, M is the identity map. So I have the identity map between two complexes, and you can check that the homology of this is 0. Okay? So this complex is acyclic, and therefore the homology of the original complex is carried by, is equal to the homology of the quotient. But in the quotient complex, well, saying that this cycle is marked either with V plus or with a V minus, but V plus is set to 0, is the same as saying that it's marked by V minus. But then what remains is simply the ordinary complex. Basically, if this ends up being marked with V minus, the only choices are how to mark everything else, and that's the same as the original complex of the other side of Reidemeister 1. Okay, so this is simply isomorphic to that. So we've shown that, so using the lemma, we've shown that the homology of the left-hand side of Reidemeister 1 is equal to the homology of the right-hand side of Reidemeister 1. So the problem with this proof, so by the way, this proof is valid. The problem is that it's a bit hard to, well, everything is symbolic and was standing for something more complicated. Okay? So you have to imagine how these more complicated things sit together, and that's a bit hard. But it's actually a valid proof. And
I have a related question.
Yeah.
So if this is homology, then a cycle is some linear combination of V pluses and V minus shifted by various degrees that vanish under the differential.
Yeah.
So this is a cycle. So what does it mean, and how does it detect the topology of the knot?
Um, in a way, this is the question that I was going to ask later, okay?
Okay.
But you could have asked the same about the Jones polynomial, or maybe you did, somebody did.
Well, I asked what it meant, and it was like, we'll think about that later was the answer.
Right. So I still would like to postpone it. Basically, you know, one of the big problems of this subject is here is an ad hoc procedure. It works. Why we should have expected it, I don't know. Okay? Yeah, so, you know, I made a decision at some point, right? I could have, after we've done the Jones polynomial, I could have turned left and explained what is the more general context in which the Jones polynomial lives. Or I could have turned right and generalize it to Khovanov homology, and somehow I ended up turning right, partially because I felt, I thought that people have heard the word and might be curious what it means. So, so I ended up going into Khovanov homology, and we'll have to go back into and we'll have to I mentioned we skipped 15 years at some point, so we'll have to go back and fill in these 15 years. Okay?
A question.
Yeah.
Yeah, I want to ask about the vector space V. So the choice of it being two-dimensional, was it forced, or we could have chosen something?
It's not two-dimensional. The dimension of V is Q plus Q inverse, and that was forced. Right? V is a graded vector space, so it's so it has a Q it is two-dimensional, right? Strictly speaking. But it's more interesting. To think of it as a graded vector space, and then it has a Q dimension, and its Q dimension is Q plus Q inverse, and this was forced because this is the value of the R naught. Okay, let's do invariance under Reidemeister 2, and again it's very easy. But again, it requires thinking, well, using symbolic notation for bigger things, okay? So, we want to show, so the left-hand side of the Reidemeister 2 is written here. Should I enlarge it? You know what? I will. The left-hand side, sorry, but that takes a second. Okay. Oh, but now, this got in the way. Okay, sorry. So now the left-hand side of the Reidemeister 2 is this complex. So these are the four smoothings that occur. Each one of them, if the original knot had n crossings, then each one of these has n minus 2 crossings. So really, this is a cube of this is an n minus 2 dimensional cube, this is an n minus 2 dimensional cube, and so on. Okay? But there are maps between these cubes. Now, the map going from this cube to that cube is always a splitting. So always a little cycle, the one in the middle, splits off from the cycle on the right, so it's always a delta map. The map going this way is always an M map, because the cycle in the middle here always merges into the cycle to its left. Okay? So that's the left-hand side of the Reidemeister 2. This has a subcomplex. The subcomplex is if you replace all of this n minus 2 dimensional cube by 0, all of this n minus 2 dimensional cube by 0, if you keep this cube as it was, and if you, using the same notation, you look at the subpart of this cube in which the middle cycle is labeled with V+. This subcomplex is acyclic, has zero homology. And the reason is that if you restrict M to V+, it's the identity map. So the identity map has zero homology. Okay? So C prime is acyclic. And so if I mod out this complex by that complex, the result has the same homology as this one. But what's the quotient? The quotient is written here. So this one got modded out by nothing. This one got modded out by 0, so it remains the same. This one got modded out by 0, so it remains the same. This one, so the top one, got modded out by everything, so it became 0. And this one got modded out by having a V+ in the middle, so you can still label the middle by a V+ or a V-, but whenever you label it by V+, you get a 0. So this is the quotient complex. Good. Now, this quotient complex in itself has a subcomplex. The subcomplex is 0, 0, 0, and on the bottom right you keep everything. Now, this one modded out, so this one modded out by the subcomplex, so in other words, C modulo C prime modded out by C double prime is this. So I took this modded out by 0, it means I didn't make any changes. I took this modded out by 0, means I didn't make changes. 0 modded out by 0 is 0, and this modded out by itself brings 0. So this complex is in itself acyclic. Why is it acyclic? Because V minus is sort of a co-identity for delta. So let me explain. So how was delta defined? Delta, sorry, I need to make more space. So delta did the following things. It took V minus into V minus tensor V minus, and it took V plus into V minus V plus plus V plus V minus. Now, suppose us here, so really delta here is the map which splits this cycle into 2, and then I take the left factor and put in it V plus is equal to 0. So suppose I mod by V plus is equal to 0 on the left tensor factor. So this one, nothing changes. The left tensor factor has a v minus on it, it just stays. So this one stays. And here, v minus tensor v plus remains, but the v plus tensor v minus becomes 0 because I modded out by having v plus on the left tensor factor. So the map delta, when you project it to this quotient, becomes the map which maps v minus to v minus tensor v minus and v plus to v minus tensor v plus. So it really inserts a v minus on the left factor, and that's all it does. So it's really the identity map. These two complexes are isomorphic, and the map delta is the isomorphism between them. So this complex has zero homology. So this complex has zero homology. But this was the quotient of these two. So the homology of this one is isomorphic to the homology of that one. But the homology of this one is simply the complex of the right-hand side of the Reidemeister 2 move. So the lesson, the moral was that the homology of the right-hand side of the Reidemeister move is isomorphic to the homology of the left-hand side of the Reidemeister moves. Okay? Then comes Reidemeister 3. So, you know, in the case of the Jones polynomial, Reidemeister 3 was a trivial consequence of Reidemeister 2. In the case of Khovanov homology, it isn't. So you either look up the proof in the URL given here, and unfortunately it involves rather complicated commutative diagrams, or, right, because both sides are three-dimensional now instead of just two-dimensional, or you wait a bit. So, you know, it was important to go through this, but I should also say that it's all wrong, morally wrong. It's wrong in the sense that well, so like the notation here stands for something bigger. This really means some horrible complex which is an n-2 dimensional cube. Okay? It would have been a lot better if we could develop Khovanov homology for tangles, like we had the Jones polynomial for tangles, and it was a morphism of planar algebras. So if we could do something similar for Khovanov homology, this would stand for itself, not for something way bigger. And then perhaps all the proofs will be easier. The cost will be that the context will be harder, because we will have to be talking about a planar algebra of complexes and things like that. Okay. You know, I wish I had time to show some computations. Maybe it will come next time. But for now, I only want to state one theorem, and I have about 20 seconds. So the theorem is the following. So this is a theorem of Kronheimer and Mrovka. And the theorem says the Khovanov homology, if the Khovanov homology of a knot K is equal to 0, then, or not precisely, is equal to the, not to 0, it's equal to the Khovanov homology of the A knot, which is just the vector space V. So if this is true, then the knot K itself is the A knot. So if you have a huge knot and you want to tell if it's the A knot or not, you compute its Khovanov homology. If it's trivial, the knot is trivial. Okay? And I'm out of time, so I don't have time to tell you why this is the wrongest. So the theorem has a proof, but the proof is the wrongest ever, and so you have a significant challenge to make it right. And that's the promised open problem from the beginning. Sorry, I'll have to quit. So see you on Friday. So I'm actually not going anywhere, but class has ended. So if you want to continue talking, we could.
Yeah, I have. Oh, sorry.
Go ahead.
Yeah, I was asking if is it a complete invariant?
No, it is not a complete invariant. So, okay, it is stronger than the Jones polynomial, but it is not a complete invariant, but it is an unknot detector.
So I had.
You just said it's an unknot detector, so this theorem is true?
Yeah, this theorem is true. Sorry, the proof is, I should have said wrongest ever in some moral sense. It uses techniques that are completely external to the subject. It's a true theorem. It's a true theorem. Sorry, you know what? Maybe wrongest was the wrong language. I should have said way too complicated. The proof is disproportionately complicated to the statement. You know, so it means that we're missing something. Yeah.
So the proofs we had for the invariance of R1 and R2 thing didn't seem to use anything too particular about M and delta, except that are restricted to V plus and V minus. They give you isomorphisms independent in the right sense.
Yeah. So
I mean, it seems like this is a part of some. You can make a better, more general machinery out of this proof technique for some slightly weirder objects where M and delta are different. Does that happen, or is there no other like M and delta? Which is related to another question I had about. Yeah, sorry.
There are very mild generalizations where you change M and delta by just a little bit. Okay? But we also use the fact that the vector space was two-dimensional, or Q plus Q inverse dimensional, right? And right, we used it because we said things like, if you kill V plus, what remains is...
Yeah, to get a cycle, you need that.
So given a two-dimensional vector space, there are just very few solutions of the equations that M and delta have to satisfy. So, okay, so there isn't a... So yes, there are generalizations, there are lots of generalizations, but they are not so obvious. You have to do things which are much more complicated.
Also, I guess the software question, Steve has already kind of talked, but on a softer note, the most surprising part for me was that we forced some definitions for M and delta, which then magically also turned out to be associative and co-associative. And is there a better way to think about why that happens and why all of this sort of fits together once you force something, more or less? I mean, we took some natural things and they worked out automatically.
Not really. I think it's just luck. I mean, yeah, I'm not aware of deep philosophy why anything commutative should also be associative in this case. I mean, I suppose the answer is the dimension is small enough, you know, so the dimension is small enough and the constraints are hard enough. Like I've used there was another constraint that we used, the fact that the degree has to be -1, right? So there's just very little choice left, and
The pigeonhole principle.
yeah,
I mean, no, it was, I guess the other option was that it doesn't work out. So I guess even in a lot of constraints, you'd expect things to fall flat or fall apart very fast. So I was a bit surprised to see that didn't happen there.
So you're highlighting that this is brilliant work of Khovanov. I mean, just to be clear.
Okay.
It is. So if you had asked anyone before 1999, first of all, nobody would think to search in this direction, and secondly, if you did search in this direction, you would be convinced that it's bound to fail. Why would it work? So yeah. Now you can ask, okay, I didn't explain yet why the Jones polynomial makes sense. Okay, why is the Kaufman bracket not a miracle? I mean, there wasn't, right, the existence of the Kaufman bracket is also a miracle. But that miracle by now I've come to terms with. I sort of understand, I sort of know why to expect it. But that's the 15 years that I skipped. Khovanov homology to me is still a complete miracle. Like, I don't know why why one should expect it. I still don't know. I don't know what problem it's so okay. Often in mathematics, things are defined by the problems they solve. So like a tensor product can be defined by it's the set of all VI tensor Vj modulo some relations, but it can also be defined by a universal property. Okay? I don't know what universal property Khovanov homology satisfies. It looks completely ad hoc. You can also, here's another weakness. So the definition of Khovanov homology is completely two-dimensional. Like the definition is you start from a knot diagram and you do something. But knots are three-dimensional things. If I give you a knot drawn in 3 dimensions, I have nothing to say about its Khovanov homology except for project it to the plane and start working in a plane.
In some sense, that's just sort of better understanding why Reidemeister moves work, right? Because in some sense, we're just bookkeeping the data given by Reidemeister moves in better ways.
Yes, exactly. This is for Khovanov homologies. There are other, there are other knot invariants that are not like that. Again, okay, so it's a lovely subject. We don't understand it yet. Okay, I should say physicists claim that they understand it. So physicists will tell you that Khovanov homology measures something very, very complicated in quantum field theory. now I'm telling you my opinions. I think it's wrong. I mean, I think it's an overly complicated way to view something that ought to be simpler, but we don't know the simpler thing yet. You know, maybe I made a mistake skipping those 15 years or 20 years, but so be it. Yes, Leonard?
I think I've seen a description of the Khovanov homology in terms of a poset, the limits of a poset or something like that. Someone described it in terms of looking in the way of homotopy groups. Then it was a little complex.
I'm not sure. I may or may not know what you're talking about, but it's not. It doesn't resolve the issues. Okay, it's.
I have a question.
Sure.
If we say that it preserves it's invariant under Reidemeister 2 moves, so now when we look at the Reidemeister 2 moves, there are 4 possible smoothings and they form a commutative diagram.
Right.
So, and two, so of these 4 smoothings, one of them is the right-hand side, and the other 3 do not look like the original knot diagram at all. And so, is there some way to see why the contributions of the wrong smoothings get cancelled out?
Here it is. That's exactly what the proof did, right? The proof, I gradually, so, you know, there was this big complex and I gradually cut off parts of it. I mean, in only 2 steps, right? I mean, first of all, I said this subcomplex is acyclic, I can cut it off. Then in the quotient, I said, well, I can mod out by something, which in itself is acyclic. So what remains is, but basically that's what I did, right? I started from those 4 things. I got down to the 1 which is the other side of the Reidemeister move by gradually chipping off parts from the rest.
Great, then that sort of is a very small partial answer to my question of like, how does this detect topology? Yeah, it does help me understand this method.
Okay. Okay. So, you know, in a way it's a bit unfair that we're speaking now for 13 minutes past the hour and some people left. So maybe we'll quit and see you on Friday. Bye.